Okay, Calculus BC, we are looking at the Chapter 12 Review 3. This is a video that we're making live in class to help students out, especially those of you who couldn't join us in class today. This problem in particular is such an excellent, good problem to take a look at. It's a wonderful type of a free response question that you could get on the AP exam also. In fact, something just like this could very well be on an AP exam. But in particular, let's read this together. This is the only problem that we're going to have in this video, but it's so important. Let's read it together. The Taylor series centered at x equals 1, about x equals 4, I'm so sorry, for a certain function converges to f of x for all x in the interval of convergence. Here is what I really want you to take note of. Look at this. The nth derivative of f is given to us in this formula. And that might look a little intimidating at first. And you could look at that and say, oh my gosh, wow, yeah, look at that. At the nth derivative of 4, it's negative 1 to the n factorial all over 4n, n plus 3. And then they're also giving us this right here, f of 4 equals 1/3. And then they're saying, let's write the second degree Taylor series about x equals 4. And actually, I'm afraid there might be a bit of a typo here. I think what I meant to type out is we'll make it a third degree, okay? We'll make it a third degree Taylor series, a Taylor polynomial, so sorry about that. And of course, right now, you could look at that and it can seem very unsettling. I've got really good news for you. This is actually a much easier problem, shockingly, than what you might have done in another context. The fact that they're telling you the nth derivative is going to be delightful. You'll see what I mean in just a moment. First off, let's just jump right in. We could say, well, for A, if I'm going to write a third degree Taylor polynomial about x equals 4, what you can do is say, starting this off, it's going to be f of 4 plus, then what? F prime of 4, x minus 4 to the first, divide by a 1 factorial. Then we'll say, take the second derivative here at 4, x minus 4 to the second power, divide by a 2 factorial. And then let's go one further step. It's always x minus where you are centered, right? If you look back in your notes from 12.10, you'd see x minus c to a power. C is where you are centered. They're telling us that we're centered at 4. And a couple of things to review and remember. No matter what term you have, if you have the second term, you've got the second derivative, you've got that 2 factorial, right? That's always going to be the case. But there's a whole nother issue at play. That is, you're always going to have x minus where you are centered. And where you are centered gets plugged into every derivative or even the original function. So this is just the template on how to get a third degree Taylor polynomial. By the way, should I keep going beyond this right now? No way. I'm not finding a series, an infinite series. I am getting a polynomial degree 3. That means stop when your highest power, that exponent, is the third power. Are we okay with that? So right now, kids are saying, wow, the only thing that we don't know are these derivatives. Now, please hear this. What I said earlier is definitely true. A problem like this is preferable to doing just an ordinary problem where you have to take derivatives consecutively. Guys, taking the derivatives one right after another, that could be some busy work for you, right? It might involve chain rules. You might have to really do quite a bit of work to simplify it. Not that it's usually all that bad, but you'd say, wow, look at that, f of 4, I know what that is. And then kids will say, but Mr. Dabner, look at this thing right here. This is so confusing looking. No, you know what? You're saying n, whatever derivative you want to plug in, if it's the first derivative, let n equal 1 everywhere in the formula. You see what we're talking about? You want the third derivative? Let n equal 3. Say, oh, is that all it's doing? Yeah, if you didn't see that before, you might look at that and say, what's going on here? So what's f prime of 4? You know what? This is where you're going to say let n equal 1. And that's going to be negative 1 to the 1. Here's a 1 factorial all over 4 to the 1 times, now 1 plus 3 is going to get you a 4. And wow, would you look at that? You could definitely do some simplifying, right? So that's 4 to the 1 right there. That's not a 4 factorial. And all of a sudden, kids could say, well, negative 1 to the 1, that's just negative 1. Down here, you'd say a 4 factorial. I mean, not 4 factorial. 4 to the 1 times 4, that's just going to get you a 16. You know what? Now you know what f prime of 4 is, what the first derivative of f is. Is that making sense so far? You'd say, well, wait a minute. I'm also going to have to get a second derivative. You know what? That means let n equal 2. It's like coming back up here. You're saying, well, what if I'm finding the second derivative? Then that becomes negative 1 squared 2 factorial. And then down below here, you'd get 4 to the second. And then 2 plus 3 is going to get you a 5. Negative 1 squared is just going to be a 1. 2 factorial is just a 2. 4 squared is 16. 16 times 5 is 80. And 2 over 80, you could say, well, that's 1 over 40. Guys, that's what your second derivative of f, when you plug a 4 in, would equal. We feeling okay with this? Notice you're not having to mechanically take a derivative. You're not doing any chain rules, anything like that. You'd say, well, wow, I want to find my third derivative. Wow, you know what? That means let n equal 3. And you get the idea. It's going to be negative 1 to the third times a 3 factorial. You could say, well, down below, I'm going to have 4 to the third. And then, you know, we have 3 plus 3 right here. That's going to get you a 6. Well, 3 factorial is 3 times 2 times 1. That is a 6. Look at that. And negative 1 to the third is a negative 1. And 4 to the third power is actually 1 over 64. We doing okay? So now look at what is happening right now. I'm going to come back to my third degree Taylor polynomial right here. And we're going to say, well, wow, f of 4 was 1/3. F prime would be negative 1 over 16. Divide by a 1, well, you're good to go. F double prime right here, you could say, well, that's 1 over 40. And you'd have your x minus 4 to the second all over a 2 factorial. And your third derivative, well, that was negative 1 over 64. And we'd have x minus 4 to the third all over a 3 factorial. Guys, that is your third degree Taylor polynomial. But I'm going to clean it up maybe just a little bit. Okay? Do you actually have to clean it up? Surprisingly, by the way, there'd be a 2 down here, bring down the 40. that would really get you 1 over 80, if you think of it that way. You could have left it simplified or unsimplified like that. Look, 64 is going to come down, but you also have a 6. So the question is, what's 64 times 6? That's going to be 384, I think you could figure out pretty quickly, whether you're using a calculator or not. And wow, here is your third degree Taylor polynomial. If they wanted me to go out further to a fourth degree, I could, and I'd do it basically the same way. We doing okay? What's new here? The new thing is that nth derivative form. If we don't talk about that, I'm sure there are many kids who would just logically say, well, I think I get what's happening. I'm going to look at this green formula right here and assume that, hey, whatever derivative I want to find, I'll just let that index go in for n everywhere and work it out. Yeah, but this is in fact the case. This is what we've come up with. Any questions on part A? Yeah. What kind of job uses this kind of math? Wow. Being able to approximate with polynomials, that could be something like immediately if you're thinking about designing things where polynomials could represent it. So some types of engineering, like computer engineering and so forth, series sneak into engineering classes later on just as well. But you, of course, can, if you're getting into pure mathematics and research, that's another area. But yeah, I mean, in terms of applications, why are we doing this? Well, this is so that we can definitely get approximations. Usually that's found either in, also actuarial science could get into that as well. If you have a big mess where an approximation might be able to represent that, that's where you could get some assistance with approximations just as well, right? So that's the quick answer, right? All right, but let's take a look real quickly. Radius of convergence. Whoa. Hold on. Radius of convergence. Holy cow. Here's what I want you to think about. The radius of convergence is tied to the interval of convergence, right? In fact, what we've seen time and time again, where I first brought that up, is you could begin to do a ratio test and, eventually get some answer like this, and this would be your radius of convergence. So if we could do the ratio test to find the interval of convergence, when we get to here and we isolate that absolute value, then we will know what the radius of convergence is. Making sense, I hope? So we need, now here's where kids will go, oh my gosh, Mr. Dobner, we need sigma. We need sigma. And while I can see what's happening here, but what's the nth term? Well, here's what I want you to remember. Sigma is going to have the nth term inside of sigma, right? So what I'm getting at is, I'm going to say it's x minus 4 to the n, right? Divided by an n factorial. And then kids will say, so what would go in front of this? Oh, your nth derivative evaluated at 4. Would you agree with that? Right? If I said, hey, remember when we went out to the third power right over here, we said, what would that look like? Well, you had x minus 4 to the third power. You had the third derivative of f, plugging in where you're centered, plugging in a 4, and then you'd say divide by that 3 factorial. You'd say, well, hey, if I've got this, if I want to be able to work this out, and by the way, right now we could even say n equals 0 up to infinity. You could say, well, wait a minute. Do I have that? Oh my gosh, that's the formula that we have in green up here. You know what that thing really is? It's this. It's negative 1 to the n factorial, all over 4 to the n, times n plus 3. Guys, that right there is your nth term. Then kids will say, don't forget, you still have to divide by n factorial. I'll let you think about that for a moment. What goes in front of x minus 4 to the n? Well, it's the nth derivative of your function, plugging in the 4. Hey, they gave us that formula. And then you have to divide by n factorial. Now, if you're really on your toes, and I know you guys are, what's going to simplify here? The n factorials are going to cancel out. Here's what I'm talking about. And we could throw in this intermittent step just to make it super clear. You'd say, when I'm dividing by any term, like look at this. We've got this right here. If I'm dividing by n factorial, that's the same thing as multiplying by 1 over n factorial. Now kids will say, do you have to show that? No. You could have just said, we know these are going to cancel. Right? We know those are going to cancel out. You know, this 4 to the n all over n times n plus 3, that's coming down. But that n factorial up above will cancel that n factorial down below. You'll say, oh my gosh, well, look at this. That means we have this right here. Now, surprise, surprise, if you want to think about this in a crazy way, and I'm not going to do this for the sake of time, we're making a video, but you could plug in 0, plug in a 1, plug in a 2, plug in a 3, work it all out and see if you get your Taylor polynomial for part A. Do you see what I'm talking about? Let me just do the third one. If it was n equals 3, you'd say, ooh, you're going to have x minus 4 to the third. Down below, you'd have 3 plus 3 is a 6. 4 to the third was 64. And you'd have negative 1 to the n was negative 1. And you'd have 6 times 64. You'd say, hey, what is 6 times 64? We worked that out by hand a moment ago. Oh my gosh, yes, we did get that. Do you see what I'm talking about? Kids will say, what about n equals 0? Plug it in and see. You plug in n equals 0, x minus 4 to the 0, it goes away. It's just a 1. Negative 1 to the 0 is positive 1. 4 to the 0 is a 1. 0 plus 3 is just a 3. Ooh, I should start with just a 1/3. Son of a gun, I do. You see what I'm talking about? This thing right here would generate whatever you need. Wow. That's pretty cool. But wait a minute, I digress. Aren't we supposed to find the interval of convergence? Rather, aren't we really supposed to find the radius of convergence? So, yeah, here's what we do. We could say a sub n is equal to negative 1 to the n, x minus 4 to the n, all over 4 to the n times n plus 3. That's unifying it, making it one fraction. A sub n plus 1 is negative 1 to the n plus 1. Here's x minus 4 to the n plus 1. Down below, we'd have 4 to the n plus 1. And n plus 1 plus 3 becomes actually n plus 4, doesn't it? And if we did the ratio test, by the way, I'm going to deliberately do something wrong right here. To say, what are you talking about? What did I forget? I forgot something serious. Yeah, you see, oh, that doesn't matter. Oh, it sure does. Oh, it sure does. You don't put that, it's like, ooh, no. Look, you need your absolute value. And you're going to say, well, first of all, I've got my a sub n plus 1. That's that bottom term that we've got down there. Right? We've got this. And then you're going to say, ooh, now I've got to divide by that nth term, this thing that you had right here. You know what? Dividing by a fraction is the same thing as multiplying by its reciprocal. Look at that. Look at that. So right now, some good things are going to happen. Real good things are going to happen. First of all, anything with that -1 to a power, ignore it. In absolute value, that won't be there. It would all become a positive one. And sometimes kids will say, but Mr. Dobner, sometimes those are positive ones. Yeah, if so, they remain positive ones, right? But would you agree with me there's one more power of x minus 4 somewhere? Where is that? On the top. Right here. Right? And there's one more power of 4 down below. And right now, you don't have to write this, but I'm just bringing this up because sometimes kids have been asking me about just the limit part. You don't have to write what I'm writing right now, but I want to very, very, very clearly tell you, this n plus 3 over n plus 4, that is evaluated from the limit, right? And what is n plus 3 over n plus 4 going to go to? Just a 1, right? Think about it. If you've got like 1 billion plus 3 over 1 billion plus 4, it's like the plus 3 and the plus 4 aren't even there, right? We're saying that gets close to a 1. And this is our limit. This is our limit right here. To converge, we want that to be what? Less than 1. And guys, right now, pardon me. Right now, if I multiplied by 4, I can tell you your radius is 4. Right? Like I wrote earlier, if you had x minus c is less than r, this number right here to the right is your radius. I've had some kids tell me before, Mr. Dobner, I'm sorry, I don't understand what a radius of convergence is. I don't get what you're talking about. Where are we centered? At 4. And sometimes kids are saying, look, I feel comfortable doing this. I feel comfortable doing this. I can add a 4. By the way, you don't have to do this. And kids will go, see, this is good. I like that. And that's fine. Hey, on the number line, you're saying you're going between 0 and 8. And then you're going to say, here's 4 where you are centered. You see that? What's the distance that you're going to move to the right? 4. What's the distance that you'd move to the left? That's why it's called the radius of convergence. It's the distance that you can move from where you're centered, right and left. That's what creates your interval of convergence. Is that making sense? Now kids will say, ooh, I better check the endpoints. No, they're not asking for that. Sometimes, by the way, I'll even let the cat out of the bag. I'm going to do this on the test. I'm going to say, just tell me the radius. Just tell me the radius. Right? We doing okay? So what could you see on Friday? You might see a derivative generator. Yeah, that could happen. And if so, I hope you're saying, these are cool. I like seeing these nth derivatives because then they're good to go. Oh, we've got one last thing. We've got one last thing here. Tell you what, I'm going to put in a little bit of space here. Give me 1 second. Look at that. All of a sudden, kids can look at that and they'll say, whoa, wait a minute. Mr. Dobner, hold on a second. Hold on a second. You erase that. Please don't. Please don't. You should go back to part A. you've got to show the fourth degree Taylor polynomial approximates f of 4.5 with error less than 1 over 1,000. Oh my gosh. Oh my gosh. Well, get a load of this. Yeah, this right here was our third degree Taylor polynomial. Okay? We've got our third degree Taylor polynomial. Could I move out to a fourth degree Taylor polynomial? Some kids would do this. By the way, this is a real AP question, and you could do that, and that's fine. That could help you. But they're not asking you to necessarily even do that. That seems so cryptic, doesn't it? They're saying show that that fourth degree Taylor polynomial about x equals 4 approximates f of 4.5 with error less than 1,000. Oh my gosh, let me show you the slick, cool way to do it. Listen, if I did, hypothetically, if I did plug in, and kids will say, this isn't a fourth degree Taylor polynomial. Oh, I know, but listen. Take a look at this. Take a look at this. I'm going to make it real crystal clear here. Tell me about the series that you are seeing right here. You could say, well, wow, it's alternating. Thank you. It's alternating. This is an alternating series. And you could say, well, this is 0.5, and you could say it's 1 over 80. But kids will say, oh my gosh, it's such a crazy alternating series. Mr. Dobner, I don't know what the next term would be. Well, you could actually generate it if you needed to, but we don't even need to. You just told me this is alternating. Now, if you looked at the answer sheet, and it's posted on Google Classroom, what you can say is, F is represented, or you could say F of 4.5. How about that? F of 4.5 is represented by an alternating series that decreases in absolute value to 0. Now, that's something that you're going to see enough. You should be familiar with that language. What I'm really saying is b sub n plus 1 would be less than b sub n, and the limit as n goes to infinity of b sub n would go to 0. Ignoring the plus minus signs, those terms are getting smaller and smaller, and they're heading towards 0. You could say by the alternating series estimation theorem, the error is bounded by the next term. And you might think, whoa, what's that? By the way, I'm going to write up in the corner what that's really saying. Add up to n terms, your error bound is the b sub n plus 1. You see what I'm talking about? Kids will say, Mr. Dobner, you're not even writing the terms out. No, you don't have to if you know what you're doing. Get a load of that. You're going to say, well, wait a minute, we're going to go up to the fourth degree. Yeah, you know what? Your error is going to go one step beyond it. You're saying, hey, I'm going to go up to my fourth term. That means go out to your fifth term for the error. Go up to the fifth term for the error. And your error is going to be less than, so how are we going to work this out? We're going to say, well, we're going to have your f sub 5 of 4 x minus 4 to the 5th all over a 5 factorial. But you know what? This x right here, we're actually going to plug in a 4.5. You see what I'm talking about? This 5th derivative, let's come back one more time up here and say, hey, this 5th derivative is going to be negative 1 to the 5 times 5 factorial all over 4 to the 5, and 5 plus 3 is 8. So you know what? This is going to become an absolute value, right? We're going to say this is negative 1 to the 5th, and we're going to say 5 factorial. And we could say all over 4 to the 5th times 8, and this is 0.5 to the 5th, and we're going to say divide by 5 factorial. Okay? And here we go again. Kids will say, could you have used your sigma to help you out from part B? Yeah, you could. Look, these 5 factorials are going to cancel out. And what are we really dealing with? We've got 0.5 to the 5th all over 4 to the 5th times 8. Let's get our calculator out and work that out. We'll say, well, let's see here. The calculator is not turning on. There it is. 0.5 to the 5th divide by, here I'm going to go 4 to the 5th times an 8. Okay, bye. Guys, that's going to be it. That right there is 3.815 roughly times 10 to the, what was it? Negative 6. And that, of course, is going to be less than 1 over 1,000. 1 over 1,000 is just 0.001, right? Pardon me. So that right there is what we just did. It's just your next term. It's your next term that caps your error. So that right there.